So thank you for the opportunity today to present the work that we've been doing at the RETHi Institute, which is the Resilient Extraterrestrial Habitats Institute. And this is a NASA center. It is headquartered at Purdue University. And what I'd like to introduce you to today is the work that we've been doing to make these extraterrestrial habitats both smart and resilient. This is funded by NASA through an STRI grant, which is a Space Technology Research Institute grant, and we're also supported significantly by Purdue University. So the human race has been thinking about space and how to inhabit space environments for a couple of hundred years. But it's only been in the last 50 years or so that we've actually realized this. The International Space Station, in fact, has only been in existence for a little over 20 years. And so we really don't have a lot of experience dealing with this extreme environment that is outer space. There are lots of concepts as to how we can build and do this in an effective and efficient way, an inexpensive way even. Some of those include inflatables. But when it comes to surface habitats, we really don't have a significant amount of experience at all. There's several concepts out there. I'm not going to show all of those concepts, but here's one from the European Space Agency. This is a concept that was developed several years ago by architects and engineers and really has not yet been tested, but it exhibits a number of the features that are necessary to keep these environments safe. We've also developed within our team a concept. It's not a design. I wouldn't say that it's a design of a habitat, but it is a concept that allows us to study the features of resilience and how to make these systems smart so that they can sustain human life and do so for many decades. We're really interested in the question of how to turn these into habitations that are not just for a decade or so, but last as long as infrastructure on the Earth, several decades, maybe 70, 80 years, maybe 100 years. So we're looking at what features are needed to really make these sustainable long term. So if you can imagine the lunar environment, it's so much more extreme than anything on Earth. On the Earth we have earthquakes and we have tsunamis and hurricanes and tornadoes and all sorts of extreme weather. We also have extremely high temperatures and low temperatures for humans anyway. But the lunar environment is so much more extreme than any of those, right? First of all, we have a vacuum. There's no way to breathe on the moon. We have radiation from the sun, from the environment. We have dust that is like glass, and it can get into your lungs, and if it does, it's going to be extremely dangerous for humans. And it's even going to be dangerous to equipment and seals, right? Seals on the habitat. We have extreme environments. The highs are higher and the lows are lower than anything on Earth. Meteorite impacts are going to be continually bombarding the surface of the moon. And there's also moonquakes. Moonquakes do exist on the moon. And they could pose a threat to lunar habitats. Is something we need to think about a little bit more. Equipment failure is going to be a constant concern. It is in the ISS, and these things happen. We have to be aware of how to detect them and how to diagnose them and how to repair them as soon as possible and as soon as it's necessary, more importantly, for the humans and the habitat to survive. And then, of course, there's biological hazards. There's the growth of bacteria happens extremely rapidly in these environments, and we have to keep everything clean quite a bit. So how do we deal with this problem? How do we build habitats that can survive all of these different extreme conditions and to deal with both the expected faults, the expected disruptions that we are continually thinking about in this environment, but also the unexpected, the things that we never expected might happen that are going to be threats to the habitat, the inhabitants of these domes, as well as the habitat itself. If you think about it, there's also another major concern. Right now, the ISS is relatively close to the Earth, and even with that proximity, that closeness to the Earth, there are anywhere from 20 to 100 people on the Earth at any given time, managing, watching sensor readings, trying to understand what is going on in the ISS, looking for faults, looking for issues that might be arising. And thus, it's really tightly linked with the Earth. The data is being sent down to the Earth at all times. We can really watch over the ISS quite closely. However, as our space habitats recede from the Earth and they become much further away, for instance on the Moon, or even worse on Mars, these habitations have to be more autonomous. And we can use the lunar base, a lunar base, as an outpost to do some exploration and some testing of ideas on how to be autonomous before we go further out, cislunar to the Gateway or to Mars, for example. So being autonomous means that in times when the habitat is crewed, there's a crew on board the habitat, in other words, there's not a need to send so much data or no data to the Earth to diagnose what the problems are. It has to be self-diagnosing and self-prognosing, okay? But in addition, there may be times when a lunar habitat will not be inhabited, and there will be no humans present, and thus it'll be completely operated by robots, and the brains of the habitat, which we call command and control, the brains of the habitat that are going to make decisions, take in sensor readings, determine what's happening in the habitat itself, and then make decisions about what actions to take to keep things going. So this distance that we have from the Earth is going to create this need for us to be autonomous. And so our institute has 4 partner universities: Purdue University, the University of Connecticut, Harvard University, and the University of Texas, San Antonio. And our mission is really to propel space exploration forward by developing new knowledge and new techniques. We're trying to focus on these 2 words, smart and resilient. So smart implies that we have some intelligence built in, some sensors, and some decision-making capabilities. And resilient means that we're adaptive. We're able to deal with all of the different hazards and disruptions that may occur. Disruptions, of course, must be managed. We don't know exactly how to deal with every disruption, and every situation may be a little bit different. But if we know the state of the habitat, then we can do that. We can make decisions and we can manage the consequences of those disruptions. So SmartHabs have the ability to do this. They can sense, they can anticipate, they can respond, and they can learn from the different things that occur to a habitat during its lifetime. We have a lot of experience with this on Earth, but we have very little experience in this environment. And thus we need to start all over again. We can take a lot of lessons from Earth, bring those into our space habitats, but we also need to think about the unexpected and to think about how we can learn from these unexpected events. The other thing we need to do is operate in either this crewed mode or this dormant mode, so that we can transition back and forth between those two safely and sustainably, but we can also be autonomous in a dormant mode. So really, this question of how to build resilient and sustainable habitats is a question about selecting, managing, and using limited resources. We're in a very resource-constrained environment here. It's going to be potentially days to weeks to years, if you're talking about the Mars habitat, before we can get another set of supplies. So we have to deal with what we have, and we have to bring the most intelligent set of tools with us. So the way that we're approaching this problem is that we define safety as a control problem. And if you think of our habitat and all of the states of all of the different subsystems in our habitat, it's moving through time in a trajectory, along a trajectory. And if it's in the safe region, everything is good. If we can use their sensors and use our information that we have to determine that it's in the safe region, everything is fine. But once it begins to show signs that it's moving outside of that safe region into an unsafe region, we want to pull it back. So our objective is to implement this like a control problem and use the concept of safety controls to bring it back along into the safe trajectory. So we need to do that with interventions, as I mentioned. Interventions could be passive. They could be things like self-healing materials. They could be active. They could be robots that actually take action and go out and do a repair action. And we view these features, these characteristics of the habitat as safety controls. We view them as our toolkit. So we want to bring along on this mission the best toolkit to ensure survival, to ensure functionality, so that we can do the science and the exploration that is interesting. So we view this as a resilient toolkit, and what that might include is things like sensors, the capabilities for fault detection, situational awareness, how do we do predictive modeling so we can make decisions that are smart, and what robots do we need in order to maintain the habitat and to repair the habitat in the best possible way. So the resilient extraterrestrial habitat is focused on these three objectives. There's three different thrusts we're organized into, and we're really focused on this question of resilience, and that is how can one adapt? How can this habitat change its course, adapt, absorb, and rapidly recover from both unexpected and expected events when something happens? And the idea is to do that without anything changing. We can still maintain the functionality and the critical functionalities, especially of this habitat. So, how do we do this? Well, the first thrust in our group is the resilience thrust, and that's about the architecture. This is about the toolkit that allows us to be adaptive and resilient, and selecting the things to bring with us, selecting the features of the habitat that make us resilient. The second one is the awareness thrust, and this is about autonomy. This is about how do we perform predictive modeling using the sensors that we have and select the best course of action when there is some type of disruption. So this is where the smartness lies in the habitat. And then there's also the robotics thrust, and the robotics thrust is focused on implementing these. We're developing technologies that would allow us to be autonomous, would allow us to maintain and repair the habitat, do the typical things that happen every day to day in such a habitat, but to do so autonomously. Our process is as follows. We have our notional real habitat. And again, this is a concept. It's not meant to be a specific design. It's just meant to be a concept that allows us to visualize and put some thought behind the different simulation environments that we're building. We're actually building 3 different simulation environments, one of which is called the MCVT. I'll explain that in a second. But the idea is to build a simulation that consists of many simulation models, many models of our subsystems that are interconnected and capture the interconnectedness, but that they also capture the damageable and repairable characteristics of those systems. With that system of systems model, we can assess resilience. We can look at different hazard scenarios, and we can assess the resilience of that particular architecture, and we can look at which features were helpful and which features really were not as helpful. And then we modify the architecture and we go through another cycle. Okay, so we've gone through 2 or 3 cycles of this, building more capabilities for damageability, more capabilities for repairability, and increasing the reality of these simulations so that we can study more complex behaviors. So this is a diagram showing the insides of the habitat. So if you took away the structure, you took away the regolith layer, the soil layer on the outside of this habitat, you would see the subsystems on the inside. The power systems, the life support systems, the sensors, the robots. Even on the left-hand side of this diagram, you see the communication network, the dishes, and you see solar panels, right? And our modular coupled virtual testbed, which is for short, we call that the MCVT. This is this is a system of systems model that consists of many subsystems as indicated there on the left. We have interior environment to capture that pressure vessel. We have the exterior environment to capture all of our disruptions from the exterior, from the hazard, from the environment. We have a structural subsystem which also includes a regolith layer. We have power generation, smart power distribution systems, agents, decision-making brains of the habitat, the command and control. And we also even have the database and ground control in our models. And so you could view this as a sort of digital twin in the sense that we are trying to capture what our notional real habitat would be, how it would behave, and what we would be doing with it. So this is the basis of our research, to build a simulation environment and study resilience and study decision making and study state estimation and all of these concepts. But there's some features of this simulation environment that need to be there before we can do those things, right? We need it to be damageable. We need the structure, the life support, the power systems, all of these subsystems essentially have to be able to be damaged. And we need a series of faults that could occur so that we can understand the consequences of each of those scenarios. We need it to also be repairable. And if we're going to study resilience, we have to allow it to be damaged, and then we also have to allow it to be repaired so that we can understand what repair rates might be necessary, what type of technologies might be needed in order to keep this habitat resilient, to keep it in that safe range. That means that we also need embedded sensors. Those are going to provide state estimation. Those are going to provide the ability to do decision making with awareness, right, with intelligence. And we also have to be able to capture the cascading effects of these hazards, of these different types of faults. So a meteoroid strike, how is a meteoroid strike going to propagate through the habitat? Well, it does depend on where it hits, right? It's not going to be the same if it hits the life support system versus if it hits the recreation area, for example. So what we need to be able to do is capture location information. So what we've been working on is a simulation environment that allows us to do this system of systems with all of these different subsystems and their interconnectedness. And they have to capture the faults and the cascading effects that will propagate through this habitat. So let's talk a little bit about some of the features of a habitat of this type. So if we take a close look at this habitat, first of all, we have to have some type of protection from the radiation. One way in which we protect from the radiation is with a layer of regolith. So this is the way that we've chosen to represent this protection. So we need vacuum. The structure protects us from the vacuum of outer space. The regolith layer is mainly to shield us from the radiation from the sun. We also need a lot of sensors, right? In deep space, NASA doesn't like to use a lot of sensors and a lot of computational power because computers are very vulnerable to the radiation too. It's not just humans that are vulnerable to the radiation, but the computers and anything that's electronic is essentially very vulnerable as well. But yet we do need sensors, right? So we need to decide, is the structure damaged? Has there been a change in pressure, a change in temperature as well? But sensors are also potentially the source of faults, right? We could get incorrect readings from them. So we need to know how to distinguish between faults and faulty sensors, right? There's also sensors for things like fire, for the interior environment, for contamination. And all of these sensors essentially they are used for diagnosis and state estimation and sent to our health management system. We're going to have robots that are going to maintain and repair the habitat. We need to do a lot of work in a habitat. Astronauts spend a tremendous amount of time just maintaining the habitat in the ISS, keeping it safe, cleaning, and especially if you're doing science, you have a lot of work to be done there. So robots are critically needed for maintaining the habitat so that the crew can use their time for science. And there's also features that we can study, such as modular designs. If we have a modular design with multiple domes, we have the opportunity to use one of them as an emergency shelter. So there's a lot of different features that we can add, but we also, as I mentioned a minute ago, have to consider the layout of the habitat. So what is the geometry, and what is going to influence the intensity of the different faults or the cascading consequences of these different faults in a habitat? So the left is sort of a high-level map showing that there might be a landing and launch site nearby. There might be a solar array nearby. How far are these going to be roughly from the habitat? And we just, started with some rough estimates to have a layout that we could study, and we can always move these around. On the right-hand side, we show what's inside of the habitat. So this is the inside. We have power systems in a particular area. We have life support in a particular area. We did this with a typical architectural design procedure where we wanted to know what was next to what, okay, to get a reasonable design that had typical features for a space habitat that had these needs for humans. And with this information, we can encode this into our models, and we can actually capture when a meteoroid strike occurs, what parts of the habitat, what subsystems of the habitat is that meteoroid strike going to actually affect. So in order to do our research, in order to build these faults and these damage scenarios into our habitat system, we considered a number of scenarios. This is one of the scenarios, and this is kind of one that we've had from the very beginning. It's focused on the question of meteoroids, and it's how do you deal with the thermal management when there is some type of meteoroid scenario. Okay, it's a common question in space problems. So on the left, we've shown one of the domes affected by a meteoroid. Okay, what happens when this meteoroid strikes is that we actually have damage to the protective layer, possibly to the structure, possibly to things inside of the structure. So at the very least, there's going to be an effect of the regolith that is going to, when it takes out regolith, it's going to have exposure to the temperatures in the atmosphere. And the structure is going to locally change temperature. If it's cold outside, it's going to get colder on the inside of the habitat and in this region of the structure. If it's hot outside, it's going to get warmer. Okay? So what we're considering is what would be the decisions that one would make and the timing, the criticality of those decisions regarding how to react to this. How do we decide? If there's damage to the structure, it's more important to act quickly. So we're thinking about those types of questions as we build our research plans. And so we're building another simulation environment, which is our cyber-physical testbed. And why are we also building a cyber-physical testbed in parallel with this MCVT? Well, first of all, we're going to take data from our cyber-physical testbed to inform our models, to make them stronger and to include all of these interconnected connections which may actually be hidden between the subsystems. We may not have thought of them, we may not have considered them, they may be unexpected failures or unexpected effects. We also aim to use our cyber-physical testbed to validate concepts and approaches using a physical model that actually has a great number of uncertainties compared to the models that we built numerically. And we want to demonstrate new techniques and technologies like robotics, but overall we're really trying to just learn as much as we can. So we're building a testbed to be versatile, to be reconfigurable, so that we can learn as much as possible about these problems and about these algorithms. So if we think about this notional real habitat and all of the subsystems that we have, we ask ourselves, how would we break this up so that it's cyber-physical? The cyber-physical testbed is cyber-physical because we have some of the systems in the physical side, they're physically in the laboratory, and other systems are in the cyber side, they're models. They're essentially models that are acting in in the computer. And so what we do is we break these up, and some of these are physical subsystems because they're needed, right? We can't have a pressure volume unless we have something to contain it. So we have our pressure system. We have a life support system, which is thermal control, pressure control, and we have a structural system that helps contain that thermal environment and all of the sensors that are contained within that. On the left, we have the cyber system. We don't need a regolith layer in the laboratory, so what we're doing is we're including that in a cyber system. We're computing how it would influence the temperature on the outside of the structure, and then we're computationally inserting that into the physical subsystem. Okay, and I'll explain that in a little bit. But we have power system, we have a communication network. All of the same subsystems that were in the MCVT model are really here, but some of them are physical. By the way, the models that are on the left can be taken directly from the MCVT to start with and updated to build a digital twin of this cyber-physical testbed as well. So how does the cyber-physical testbed work? We have a real-time machine. It's operating in SpeedGoat. It runs all of these models, all of these computational models shown here. That interacts with our physical subsystems. I'll show you a little bit more about the physical subsystems in a moment, but this is essentially what the laboratory looks like right now. We are in the process of completing the dome that you see sort of in the middle, the grayish colored dome, and the thermal management system, which consists of the box shown in front of it and the heater that's on the inside of it. And we're planning to use this, the data from this, for the experimental validation of many of the different techniques that we're working on. So what does this look like? Here you can see the gray structure contains an air bladder that we can pressurize up above sea level. It actually has a thermal control system as well. It has a pressure control system that, just like the ISS would have a pressure control and a thermal control to keep the pressure and the temperature appropriate for human life, we have those systems built into our habitat, into our cyber-physical testbed. We also have the computational models are going to be housed in the box shown in the middle of the screen right now, which is our data acquisition system, our control room, and has the ability to run the computational models and interact with our structure. But what we're going to be doing in order to implement the thermal effects of the regolith on this dome is we're going to be covering this dome with a series of what we call thermal actuators. These thermal actuators will allow us to locally change the temperature of the dome to replicate what really would happen in the real world, which is the temperature would change on the outer surface of the dome when there is a meteoroid attack, a meteoroid strike of some type. We have pressure valves where we can actually release some of the air and create controllable leaks in the habitat so that we can look at leak detection. We can look at structural health monitoring questions of how is the structure damaged, and we can look at replicating this in this thermal effect in a cyber-physical testbed. So I mentioned transfer systems. In this case, the transfer system is this thermal actuator. Okay, so the thermal actuator is imparting upon the structure the temperature that would be on the outer surface of the structure if it were in a space environment. Okay, it's not exactly that, because I have to admit we're down to cryogenic temperatures of about minus 60 degrees Celsius. We're not at minus 200 degrees Celsius. This is very similar to the concept of real-time hybrid simulation, right? In real-time hybrid simulation, we have a computational model and a physical model that are interacting through a hydraulic actuator. Usually it's a hydraulic actuator of some type. So the hydraulic actuator is imposing the displacements on the structure that is physically in the laboratory that it would experience if it was part of a larger structure. We're doing the same thing, conceptually, but we're doing it with the thermal loads. So the thermal loads are being imparted by this thermal actuator, which consists of a panel applied to the outside of the structure with this cryogenic fluid running through it. We change the temperature of the fluid to change the effect on the structure. We also do, though, have pressure. So we have to open up valves to the right level in order to replicate what kind of leak we would want to do an experiment with. Okay, so in a way, that's another transfer system, but it happens so fast that we really don't have to think about the dynamics of that particular device. But you can see that there's a number of sensors are needed, there's a control algorithm that's needed, and we have to have a network that communicates between these two, the physical side and the cyber side. So let me tell you a little bit more about this thermal transfer system. This is something we've realized in the lab. We're controlling it. We haven't yet done acceptance testing, but the concept is that we have an experimental subsystem. I'm using a pressure box here to explain the concept. Okay, we actually do have a steel box. It's about 1 meter by ½ meter, and it can take up to an atmosphere of pressure above sea level. That's our experimental subsystem. That represents the habitat. We have a numerical subsystem that's in a computer running in real time, and that's the lunar regolith layer. And the input to that would be the temperature in the outer atmosphere, outside of the regolith layer, the temperature on the surface of the moon, essentially. The numerical subsystem and the experimental subsystem interact. We send temperatures from the numerical subsystem to the experimental, and we send fluxes back. And the idea is this thermal transfer panel is going to enforce the temperature on the exterior surface. We do that through a chiller, and this is a chiller that it's cryogenic. It goes down to about -60 degrees Celsius to positive 50 degrees Celsius, and we connect it to the thermal transfer panel, and we're characterizing this. In a control loop, this is essentially what it looks like. So we have the physical subsystem on the left, and it's a numerical subsystem. We have to impose a control system to change the temperature of the fluid and control the plant, which is the thermal actuator combined with that physical subsystem. We also have to do some state estimation in order to figure out what kind of flux is coming back so that we can account for that in our models. Eventually, we will take our dome and replace this pressure box in the next few months with a dome that has these transfer panels put on the outside. So what are the features that make this helpful and useful for our research? Well, this cyber-physical testbed can be configured in many ways. One day it can be the moon, and a different day it could be Mars, right? So the idea is that we could do different experiments with the same testbed and rapidly switch between these different experiments. We also have the ability to insert controllable uncertainties, insert faults that we know and faults that we don't exactly know how it's going to propagate through the system, but it also leverages the different models that we've developed in the other simulation environment. So now that I've introduced you to the cyber-physical testbed, let me give you a little bit of information about different research that is in progress right now that's relevant to this particular conference. First of all, Dr. Yuguang, who is in Singapore at Nanyang Technical University, is working on detection and localization of impacts. And what he's trying to do is to use CNN classifiers in order to detect these impacts when they occur. And he's including the modeling errors, he's including different sensors and turning them on and off, and he's essentially allowing for a fusion of information between the different sensors so he can determine which sensor set are the most appropriate for this particular problem, for detecting damage in this particular problem. Dr. Alana Lund is going to be starting at the University of Waterloo in Canada in a couple months, and she is working on a variational filter, and her focus is on predictive modeling. So what she's really trying to do is to take data from structures or from the pressure vessel and use that information in a filtering-based approach, so essentially in near real time, to determine the parameters of the model, to do model identification. And right now she's doing this on a nonlinear device called an energy sink, and this is a view on the right-hand side of what that is. Zishan Wang and Professor Jahanshahi at Purdue University are working on autoencoders and sensor fusion. They started with the ASC benchmark problem. It was developed about 20 years ago, and have looked at how to deal with uncertainties and how to deal with different levels of damage, and are capturing this type of information with an autoencoder. But they've also been looking at how to apply that to the structure that we have. We have another structure in the lab, and to detect when is one of the structural elements, when has it been removed. And they are looking at removing a strut and determining when and where that particular strut has actually been removed. And we're also looking at the question of leak identification and quantification. I mentioned pressure leaks, and the pressure box that I mentioned is also here on the right-hand side. We have a mass flow rate meter, and we have a pressure regulator, and the idea is that we can create a controllable leak. And using the physical equations, the physics-based equations, we can determine when has that leak occurred, and more importantly, how large is that leak, okay? So that's the question that we're trying to determine there. So those are just a few samples of research that people in the Institute are working on. But, you know, in conclusion, let me just say that this has been a very interesting problem to tackle. It's very related to this community and the structural control and health monitoring work that is out there in the larger research community, because these habitat systems have to be safe and they have to operate as intended. So if we're trying to understand the current state so that we can use that to make decisions, it's very related to this particular community. The question, though, of course, is limited resources and how to make decisions. So autonomous operations are really going to be important to making this possible. In extraterrestrial habitats, humans are not always going to be present, and it's not always going to be possible to talk with the Earth. So we really need to have that ability as we grow these systems over the next several decades to be able to do that. And cyber-physical experimentation, we feel, is one of the ways that allows us to really to do the research needed to solve some of these problems, and to do so in a less expensive way than doing it, for instance, on the ISS or some other environment like that. So with that, let me say thank you. And our website is here. If you are interested, it's pretty easy to find. RETHi at Purdue. You can go ahead and find the website and see some of our previous publications and videos that we've created about the different models. And with that, thank you very much.